So the first thing I need to tell you, I should have told you this at the end of last time, but this will make more sense out of a couple of the homework questions. Gauge pressure versus absolute pressure. Gauge pressure isn't really something we're going to talk about much in this class, but it comes up sometimes, and so I wanted to connect those two. The relationship between absolute pressure and gauge pressure is just the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. This is all we care about in this class. This is what we're going to use in all our calculations. And so let me just go through a little bit of one of the problems from the homework assignment. So let's say that we have this box and the length of the sides are 0.35 meters. And let's say that we want to calculate, let's say we're given, everything was in PSI. What is, can someone just Google, like, convert, what do we need, 100 PSI to pascals? Okay, thanks. 89,000 pascals, and then the other number we use is 14.5 psi. That's just atmospheric pressure, so I assume that's 1.01 times 10 to the 5th pascals. And we're given in this problem that inside the box is a gauge pressure of 100 psi. And so let's draw a free body diagram, and it asks a bunch of questions about equilibrium. Let's think about a free body diagram of one face. It doesn't matter which one, they're all the same. So I'm going to do it from the side, where this is outside the box, this is inside the box. So outside the box, the pressure is just atmospheric pressure. So we have forces pointing in. How do I know that the pressure is applying a force in that direction? That's just what pressure does. It's always, at any point, if you draw a tangent to the surface, it's always perpendicular to that tangent, it's always pushing. So perpendicular to this surface for the gas on this side is pushing this way. And the magnitude of that force is the pressure times the area. So that's a pressure of, since this is outside, that's the atmospheric pressure. 1.01 times 10 to the fifth. This is in SI units now, so I can multiply these numbers. And then what's the area? It's a cube, so it's just the side length squared. Can someone multiply that? What? Oh, okay. And then times the other thing. So it should give a pretty big force. $12,372. And what units is that? We have a pressure times the area. That's a force. Everything's SI units, so this is newtons. Okay, so that's a lot of force pushing in. Now let's calculate the force pushing out. So the gas on the inside of the box is pushing out. What's the force there? Well, that is a gauge pressure of 100 psi, so that's 6.89 times 10 to the fifth. But that's a gauge pressure, so we also have to add on the atmospheric pressure. Anytime you have gauge pressure, you have to add on atmospheric to get the absolute. And then that's multiplied by the same area. So can someone multiply that out? This is going to be the force applied pushing out on that face by the gas. $72,030. Okay, newtons. Oh, okay. It's going to be bigger. 96,775 newtons. Okay, so this is a free body diagram. We have a way bigger pressure pushing out than in. Does that mean that this is going to accelerate? The answer is no, not necessarily, because we're still missing one type of force. What other kind of force would be acting on this face? Whatever forces are holding the box together, it's so, if you applied this pressure difference to a box made out of paper, it would explode. If you did it to a concrete box with walls this thick, it wouldn't. So the difference is just the forces applied by the welding or the glue or the nails or whatever. And so I'm just going to put that like, let's see. So we know that that force is going to go this way. I'll just write that as F. So call that the contact force, forces from the connections. And if it doesn't explode, if there's no acceleration, we can calculate what that force is. Newton's second law says 12,372 plus F minus 96,775 is equal to 0. So F is equal to 96,775 minus 12,372. Can someone tell me what that is as a number? 84,400 what? 03? Okay, newtons. Okay, so from that we can tell, how strong that box would have to be. That's the force that box needs to be able to apply as a contact force, the weld or the whatever, in order to not explode when this force is applied. Any questions about that? Yes. Yeah, I ignored that, but yes, you would have to take that into account. So if, and yeah, I mean, it could be a big difference if if the walls are this thick, then you'd be multiplying on the inside by a way smaller area. You're right about that. I just ignored that. But any other questions? Okay, so this kind of problem is really yes. Mm-hmm. Well, the one on the outside would be acting on the whole face, and the one on the inside would just be acting on the little bit there. So, I was going to say this kind of problem isn't something that we're going to be doing in this class, but pressure is going to come up in mechanics classes for you, the people who are doing civil and mechanical and aerospace and stuff. And it's going to be sort of tricky at times to figure out the connection between thinking about pressure in terms of forces and using Newton's laws and stuff versus thinking about the pressure in terms of, state equations and stuff, ideal gas law. But this is how pressure works if you have to think about it in terms of forces. Did you have a question? Or? So before I go on, the next thing I'm going to do is the first law of thermodynamics, conservation of energy. Anyone have any other homework questions, or you have a question about this? Yes. Every face would be the same except different directions. The face down here would have atmospheric pressure pushing up, and if it's sitting on a table, it would have the table force and downward force. Any other questions, homework questions? Okay. So now we're going to go on to the first law of thermodynamics. And the first law of thermodynamics is just conservation of energy. And it's really conceptually the same thing as what you've used in Physics 1, but it's going to look different because of our strange new sign conventions. Okay, so let's start with, in Physics 1, conservation of energy looked like this. And let me sides actually. So Okay, so let's say the change in energy is equal to the work. Okay, so that's what we're going to start with. And the energy was equal to the kinetic energy plus the, I guess it could be a few different types of potential energy, but let's say the potential energy. And the work, W, is all the work done on your chosen system so that's the object that you're isolating by non-conservative forces. Okay, so what's the conservative, non-conservative thing? Do you remember? Anyone remember what a conservative force is? No, it's all work done by outside things. So conservative forces are forces dang it. Oh, son of a that is definitely on the right track. Yeah, the very simple. I have to find all my stuff again now. Oh, here we go. That's gonna be it. Nope. I was watching that bodybuilding video. Okay. All right. So conservative forces are forces where if you know the object's location, that's enough to know what the force is. The big one that you use the most is gravity as a conservative force. You also did problems where you use springs. Forces applied by springs are conservative forces. And then other things like magnetic fields, electric fields. Okay, so how does that work? Let's think about it. And yeah, this is good stuff. This isn't really like so like directly applicable to this class, but this is stuff that'll make you like, you can sound really smart when you talk to other people, you know, about conservation. Okay, so let's think about, so we know the mass of this wavelet, okay? Do you know the force that gravity applies to it if I tell you its location is here? Yes. In fact, the way we treat gravity when you're close to the surface of the Earth is you don't even have to tell us where it is. We know what the force is. It's just energy going down. So, okay, gravitational force is conservative. Now imagine there's a spring connected to the wall, and you know the stiffness of the spring. And now I tell you the stapler is here. Is that enough information to know the spring force? Yeah, because you know how far it's stretched from its equilibrium length, and you know the force is that way, and so you're good. So now let's think about some that aren't conservative forces. Okay. What about the normal force? At first you might think, well, yeah, because we know what the shape of the table is, you know, so maybe that is conservative. But think about the difference between this, the normal force right now, which is equal and opposite to the weight. And now if I push down on it, the normal force, it's still in the same location, but the normal force is gone on. So normal force is not conservative. And then what about friction? Well, friction is not conservative because it could be here sliding this way, for example, and the friction force would be like that. And it could be a dislocation sliding this way, and the friction force would be like that. Yep.
So basically, a conservative force is anywhere where a free body diagram, the only variable is the location of the object?
You could always calculate the direction and magnitude of the force based on the location. That's right. So that's what a conservative force is. And the thing that conservative forces do is it makes the force that's applied path independent. So we said we knew what the weight was here, you know. What's the weight force on this if I do this a million times and then put it here? It doesn't matter, you know. And the same with the spring. What if I go and finally put it here, you know? That didn't change anything. We still know what the spring force is if we know the location. Yeah. That's the idea, is that path independence. And what's useful about conservative forces? For conservative forces, potential energy is defined, or can be defined. Okay, so it makes no sense to talk about potential energy of a force that's non-conservative. You can't talk about the potential energy of a friction force, but you can talk about gravitational potential energy or spring potential energy. Okay. And I know what you're thinking, like, okay, but why is that useful? Well, that's where I'm going. Okay, so what's gravitational potential energy? So potential energy, I'll call that capital V. So gravitational potential energy is mgh, good. Spring potential energy, one half k x squared, where x is how far you are from the equilibrium length of the resting length of the spring? Well, why is that useful? And the answer to that is it gives you an easy way to calculate the work that those forces do. The work done by a conservative force is equal to the negative change in potential energy. Yes?
Why are you using capital V?
I didn't know what to use. I don't remember what I used later.
I'm just curious.
Yeah.
I usually use
Classical capital P.
I'm just curious.
Yeah. Let's use the U isn't good either. I don't know. I don't remember what I'm going to use later. But sometimes you see it as U, sometimes you see it as V. It mostly just depends on the calculations you're doing. Do they have other U's or V's in them? Okay, so potential energy is just a way. So, and what does this say? Well, what if you had to calculate the work that the friction force does as every instant of this path that it takes would matter, right? You'd have to include the entire information about the entire path in order to calculate the work done. Does that make sense? That, because if I take a different path, I've changed the direction of the friction force, and So in general, if you're calculating the work done by a force, you need to know everything about the path that it's taken to get from the beginning of the motion to the end. With conservative forces, you don't, because of that path independence. What that equation says is if you want to calculate the work done by gravity, as this thing goes like this 20 times and then ends up here, okay? All you have to take into account is the potential energy at the beginning and the potential energy at the end, which is obviously a lot easier than doing this crazy long integral, taking the whole path into account. Anybody have any questions about that? This is all just sort of background, actually. But yeah, like when you transfer to the U, having a good, or wherever you're going, having a good explanation of something like that for when you first, work on projects with people, they'll be like, oh yeah, I want this person in my group, and that's good, So you need stuff like makes you sound smart. Okay, so let's do a example of a conservation of energy mechanics problem. Was that like editorial? Okay, so let's say we have a skier. And we have a hill that's 15 meters high. And the skier starts at rest. How fast will the skier be going at the bottom? Okay, so we're going to use this equation that says the change in energy is equal to the work and the change in energy is equal to the change in kinetic energy. I'm going to use T for kinetic energy. Plus the change in potential energy. Okay, we're going to ignore friction. Okay, so let's think about what this skier, like, so here's like a representative moment during this run. We're ignoring friction, so no air resistance either. What forces are acting? That's right. So there's a weight acting down, and then there's a normal force. Anything else? That's it. Which of those is conservative, which is non-conservative? Normal is non-conservative. I really should have turned my email off. MG is conservative. And when you did problems like this, I mean, just like remember back doing problems like this, did the normal force come into the calculation in any way? Do you remember why that is? So, yeah, so it has to do with the definition of work. And because of the way work is defined, it's a line integral, so it's an integral of a dot product between the force and the instantaneous path. I don't know if you remember doing that. But anyways, the normal force is always perpendicular to the path. So even though it's non-conservative, it doesn't do any work. Okay, so that's lucky. So this does no work. And so the work energy principle, or conservation of energy, says the change in kinetic energy, that's, so the change in kinetic energy is 1/2 times the mass times the speed squared at the top of the hill minus 1/2 times the mass times the, that's a speed, plus mg times the height at the top of the hill minus mg times the height at the bottom of the hill. And what's the work done by non-conservative forces? The only non-conservative force was that normal force, so this is 0. Okay, so we have, this goes away, because the speed at the top is 0. This goes away because we'll call the height at the bottom 0. And so we get -1/2 mass times the speed at the bottom squared plus 9.81 if we're doing it in SI units times the height at the top, which is 15, times the mass is equal to 0. You can divide both sides by the mass, and you get that V is equal to 294.3, I think, square root. Is that right? And what do you get for that? What's the square root? Okay, meters per second, so 35 miles an hour. Okay, so you've done all this stuff before. The only thing that's sort of different is this new format, but this is the way we're going to think about it in this class, so that's why I wrote it like this. But the change in energy is equal to the work, and the energy that we're talking about is potential energy plus kinetic energy. Okay, in this class, so there's the same idea in this class, except we're going to include thermal energy. And there's going to be a new sign convention. And the new sign convention you can think of it as being based on a heat engine. Okay, so what happens in a heat engine? So if you have a piston, and there's a gas here, if you increase the temperature of the gas, what you're doing is adding heat to the gas, or let me say it as you're adding energy to the gas through heat. And what do you get out of it when you add energy to the gas as heat? So what does this produce? It, yeah, we're not going to deal with combustion, but it's the same idea. So if you increase the temperature of the gas, it increases the pressure, and that pushes the piston up. And so what you get out is work. So energy is given from the gas to the surroundings through work. So in thermodynamics, you know, if you're talking about a heat engine, you're expecting you're expected energy to be added to the gas, your system, through heat, and you're expecting energy to be lost from the gas through work. And so, so in thermodynamics, positive heat means energy is added to the gas. And positive work means energy is moved from the gas. And so doing that, you can do exactly the same, you know, the first law of thermodynamics. Says that the change in total energy is equal to Q minus W. And the only reason that you have that W is because W has the opposite meaning of what we're used to. It's still saying the same thing that it did in conservation of mechanical energy. And then that energy, so, oh, this is the heat. I said that, yeah. Okay, so this energy now is equal to kinetic energy plus potential energy plus a new thing called internal energy. And that's the new thermodynamic, the new thermal energy. Okay. Anybody have any questions? So this is the first law of thermodynamics. This is what we're going to use. There is one kind of work that we are going to use all the time. One kind of work we'll always use. And that is the work done by a gas in expansion. And we're going to think about it in terms of a piston. Although the result is more general than that. Okay, so let's say that we have a cross section of a piston that looks like So here's the cylinder. And there's the piston. And then there's a gas in here. The cross-sectional area of the cylinder and of the piston. So not the whole outer. The cross-sectional area is A. And we'll call this height H. Then the work is equal to an integral from the height at the first instant to the height at the second instant of the force multiplied by the distance that it travels. If it's positive, it's in the same direction. So what's the force that gas applies to the piston? It's the pressure times that cross-sectional area. And the distance that the piston travels in an infinitesimal increment is dH, and then we're going to integrate over the whole thing. And you can rearrange this. So H1 to H2 is equal to P times A dH. And A dH is just an increment in the volume. And so, this is, you can think of this as the volume. And so the work is equal to the pressure times the volume as you go from volume 1 to volume 2. Okay, so that's gonna apply in every problem we do in this class. When can we compute that integral? Well, what you need to compute it is, so at every intermediate volume that we're talking about, you need to know what the pressure is at that volume. And so at a minimum, we need P to be given as a function of V, okay, for us to do this calculation. So we need our pressure to be written as a function of volume. If we have that, then it's just a matter of computing the integral at that point. And it's easiest if the pressure is constant, so we'll do a few examples like that at the beginning. Okay, so let's do a couple examples. So let's say that there's a gas, the pressure of 1.30 times 10 to the 5th pascals at a volume of 0.35 cubic meters. And then the temperature is reduced as the pressure is held constant. Okay, so think for a second about what would happen. You can always, even though these are general results, the math doesn't depend on the way that you do it. You can always think of this as a gas inside a cylinder with a piston. So you start out with gas having 0.35 cubic meters of space and that pressure. What happens if you reduce the temperature of the gas while keeping the pressure constant? That's right, the volume goes down, yep. And you can think of, like, what's a way that you could hold the pressure constant? That sounds sort of complicated. We're going to keep the same amount of gas locked inside, but that is one way you could do it. Yeah, exactly. If that piston is only being pushed down by, like, well, yeah, the piston would go down no matter what. You're right. If you have it set up where that piston is being held in place by the atmospheric pressure, then that atmospheric pressure isn't going to change, you know. And so as the temperature goes down and that gas wants to have a smaller volume, the atmospheric pressure is just going to do that for you, and the pressure is going to stay constant. Okay, so now let's say that when that happens, the volume is reduced to 0.20 cubic meters. What's W for the gas? Okay, so the work done by the gas is the integral of the pressure dV, and we know the boundaries of the volume. It starts at 0.35 and it ends at 0.20. Since the pressure is held constant, we can pull that outside the integral. And so we just get, so we have 1.30 times 10 to the 5th, and then the integral of dV from 0.35 to 0.2. And so that gives 1.30 times 10 to the 5th times the quantity 0.2 minus 0.35. And you get a final value of negative 19,500 joules. So let's think about that sign in terms of the new sign convention that we have. So think of the heat engine. So this is W, and the sign convention says that W is positive if the system that you're isolating is doing work on its surroundings. So think about okay, so which way would the piston have to move for the gas to do positive work on its surroundings? Up. Yep. And so what this means is that the piston is going down. Okay. So the negative means that the surroundings are doing work on the gas. So notice if a gas expands, W is always positive. If the gas contracts, W is always negative. Any questions? Yeah.
I was just, could you think of it also in terms of like heat, whereas if you have a gas expanding, you might be putting heat in it.
Well, I would not think of it that way because there are other interactions going on, you know, like you could have changes in internal energy. So you don't know that there's, so you don't want to think about it as telling you directly what's happening with heat. Yeah. Mm-hmm. There's a lot of ways. So really, I would just think about it that way because there's a lot of ways you can make a gas expand or contract. Mhm. Oh, so in thermodynamics, we're going to use it for anything, but mainly our system is going to be a gas. And mainly we can think of it as a gas inside a cylinder like this. Okay. Any other questions about that? Okay, let's do another example. Okay, so this time, let's say that we have sort of these two rooms with a sliding door in between them. Okay, so you have gas 1 over here, gas 2 over here, and you can think of this as a piston or a barrier that goes back and forth, changing how much volume each one of those two rooms has. Gas 1 has a pressure of 1.0 times 10 to the 5th pascals, and gas 2 has a pressure of 0.6 times 10 to the 5th pascals. And let's say that we maintain both of those pressures constant. As V1 goes from 0.1 cubic meters to 0.15 cubic meters. Let's see. And the total volume in both of them is 0.2 cubic meters. Okay, so what happens is, let me draw it the other way. So this barrier starts out here and moves all the way over here. Okay. So gas 1 goes from its initial volume to 50% more volume. And gas 2 then, its volume is going to go down. And we want to calculate a couple of things. So first, what if the system that we're isolating is, so if our system is gas 1, what's the work? And then second, if our system is gas 2, what's the work? Okay, so first of all, for A, so now imagine that we're isolating gas 1. What's the sign going to be for W? Is it going to be positive or negative? Positive because it's expanding. And for gas 2, since it's contracting, W has to be negative. So in terms of what that sign means, if gas 1 is expanding and it has a positive sign, does that mean it's giving off energy through work? Or is gas 1 gaining energy through work? It's giving energy away. If that W is positive, think about it as like a heat engine. Okay? If W is positive, it means energy that was in the gas is now being given away through mechanical work, like a heat engine does. Okay, so the first one, part A. So W is equal to the integral of P dV as the volume goes from 0.1 to 0.15. Again, we're keeping the pressures constant. What would you have to do to gas 1 to keep that pressure constant as it expands? You have to do something to its temperature. Would you have to raise it or lower it? Raise it, yep. And then for gas 2, it's, the opposite. If that's going to stay at its same pressure while you decrease the volume, you're going to have to decrease that temperature. Okay, so the work is equal to P is constant through the whole thing. Whenever that happens, we're happy because we know we can do that integral. We don't need to look for any other relationships. So we have that pressure times the integral from 0.1 to 0.15 of dV. And so that's equal to 1.0 times 10 to the 5th times 0.15 minus 0.1. And you get negative I'm doing the wrong one. Yeah. So what do you get for this? That's positive 5,000, I think. And SI units for energy are joules. I think I had it written backwards on here. Any questions about that? So that gas was expanding and we got a positive W. On my notes, I had the barrier going the other way. So sorry about that. But this is how it is. And now for part B, now we're isolating the other gas. The work is equal to the integral from, so this one starts at 0.1 and decreases to 0.05. The pressure so PdV. Constant pressure for that gas is 0.6 times 10 to the 5. And we're multiplying that by the integral from 0.1 to 0.05 dV. And so we get 0.6 times 10 to the 5th times 0.05 minus 0.1. And you get negative 3,000 joules. And the signs work out like we predicted they were going to work out. Yes?
So assuming over the whole system, you would have to, in order to have this occur, you need to add 2,000 joules of energy.
That's exactly right. So this can't happen, isn't going to happen spontaneously. You need a motor or something pushing this barrier in that direction. In addition to the fact that we don't have a way to calculate what's going on with this yet, but we know intuitively, in addition, you have to heat up this gas and cool down that gas. The whole volume is 0.2. And so if this one at the end takes up 0.15 cubic meters, there's only 0.05 meters left for the other one. Okay. Now what if you don't have constant pressure? Well, somehow or other, you need to be able to calculate the pressure as a function of volume. And so sometimes you can have experimental results that'll tell you what the relationship between pressure and volume are as a process occurs. So we're going to assume that the pressure times the volume to the 1.2 power is equal to a constant. During this process. P1 is equal to 3 bar, and that's 3, the meaning of bar is 3 times 10 to the 5th, no, 3 times 10 to the 7th pascals. 1 bar is equal to 1 times 10 to the 7 pascals. And V1, the starting volume, is equal to 0.1 cubic meters, and the ending volume is equal to 0.2 cubic meters. And we want to calculate W. Okay, so we know at instant 1, we know that the pressure is 3 times 10 to the 7 pascals, and we know that the volume is 0.1 cubic meters. And then we know at instant 2, the pressure, well, we don't know that one, and we know that the volume is 0.2 cubic meters. That is, so that's saying that experimentally we know that during this type of process, if you multiply the pressure and the volume to the 1.2 power together at any instant, it's going to be equal to a constant. Okay. Yes. Yes, you're right. I was thinking of kilopascals. It should be fit. Okay, that's all right now. So we know that the pressure times the volume to the 1.2 power is equal to C. So we can multiply both sides by V to the negative 1.2 power and get pressure by itself, and we have C times V to the negative 1.2. That's the relationship. We just need to find that C. And we can do that from what we know at instant 1. At instant 1, we know that 3 times 10 to the 5th is equal to C times 0.1 to the power of negative 1.2. And that tells us that C is equal to 18,928.7. So now we know this relationship. P as a function of the volume, and that's the thing that we needed to do this integral, is equal to 18,928.7 times the volume to the negative 1.2. And now the work is equal to the integral from the starting volume to the ending volume of 18,000, question? 18,928.7 times V to the negative 1.2 dV And so that's equal to, well, go through that integral and you end up with 19,417.4 joules. Any questions about that calculation? Yeah, so you need to know something about that relationship because, yeah, you need to have the pressure as a function of volume. Like later on, we'll know some rules for that, but for now, like you'll just have to have an experimental result. And last thing, and get in the habit of doing this on each one of these calculations, mostly just to get that sign convention straight in your head. Does this make sense with the sign convention? W is positive. Yep, the gas is expanding, so W is positive. Okay, see you Thursday.